This video is going to deal with entering radial flow into a spreadsheet model. We're going to start by developing the 2D flow for the spreadsheet model and then extend it for radial symmetry. This is the numbering that we'll use for grids in plan view. And in this sense, we're looking at the flow into cell 5 from 1, 2, 3, and 4. And we see that the total is equal to 0. And the flow from any cell into the center cell is a function of the cross-sectional area, the hydraulic conductivity or effective hydraulic conductivity, the length or the cell width or height, and the head difference. If we combine these two equations, set them equal to 0, and then we solve for the head in the center cell, we get this relatively ugly looking thing that relates all of the areas and effective Ks and sizes of the cells to that head in the center cell. If all of the cells are square and they're the same size, then the area and all of the distances are constant throughout and they divide through. If we further assume homogeneity, then that means that the K is the same everywhere, and it becomes a simple case of the head in the middle cell is the average of the heads in the surrounding cells. So what changes if we think of this in radial coordinates? We still have that same map view, so we're looking for the flow into cell 5, but now we can see that the cross-sectional areas facing each side of that cell may be different, and we have to account for that. The partial circumference on the interface is that inner radius RL times d theta, which is the angular rotation of that wedge, and similarly for the outer edge A35. So if we multiply each of those by the height dz, we have the area of those two faces. For the top and bottom from 2 and 4, we're coming through that partial ring. So we need the area of what the entire circle with radius r sub r would be minus the area of the circle with r sub l. And we end up with this equation for those two faces, the area of those two faces. Finally, we need the distances between the centers of, say, cell 1 and 5 and 2 and 5. In the radial direction, that's your dr, and in the vertical direction, that's your dz. It's worth noting that flow is still only 2D here, even though it seems like a 3D system, because there is no flow around the well, only vertically and towards the well. Going back to our cell equation for H5, if we make the substitutions for the radial geometry, we end up with a more complicated looking equation. But then we can start to make some simplifications. For instance, the d theta appears on the top and bottom, so we can remove that. And then we end up with this simpler form. And if we assume that domain is square in the sense that dr equals dz, it becomes even simpler. Finally, if we assume homogeneity, all of the k terms drop out, and we get the simplest form yet. For the last step, we're going to define a term that collects all of the geometry, and it'll just make it simpler to write this in a form that we can make sense of here. So we have this geometry term and then the heads in the surrounding cells. And if we plot these as a function of radial distance, what we see is that the relative weight on the head on the left and right and top and bottom changes as a function of distance from the well. So this is essentially a weighted average problem, and when we're close to the well, we are overweighting the inner cells relative to the outer cells because the area, the cross-sectional area towards the well is so much smaller than the cross-sectional area away from the well. So we are much more sensitive to the head in that inner cell. So what have we learned about radial flow? Well, as with any solution of the flow equation, we're summing all of the flow into a cell or into each cell and setting that to 0 for steady state. If we have a regular grid in homogeneous conditions, then for regular rectangular grids, the head in the center cell is simply the average of the surrounding cells. What changes fundamentally for radial conditions is that the area of the faces towards the well, or towards the symmetry, point of symmetry, are smaller than the faces away from that point, or farther from that point of symmetry. The result of this radial symmetry is that the gradient is higher towards the well, near the well, but as you move farther away, the difference in areas from the inner and outer faces are very small, and so it essentially approaches a rectangular grid.